Lesson 10, we're going to delve into rational numbers, ratio numbers, whatever you want to call them, and equivalent fractions. Fractions a very related topic. It's a lengthy one, a lot of review, maybe some new things as well. Let's get into it. They show a loop, an oval-looking thing that lists the whole numbers. Remember, whole numbers start with the number 0. Right here. Okay, and it goes on to the right of 0. Okay, if we multiply two whole numbers, is the product a whole number? Yes. Any whole number times its, any other whole number is going to still be a whole number. Any whole number that you add together is going to be another whole number. Because that's true, we say that whole numbers are closed under addition and multiplication. Meaning, when you use 2 from the set of whole numbers to add or multiply, the solution will also fall under that category, that set of numbers, that type of numbers. Now, not every operation works. Let me show you. It's not closed under subtraction. Why? Because under subtraction, you could subtract a bigger whole number and get a non-whole number, such as 2 take away, how about 3? If it's bigger than the first number, why is that not a whole number? Because the negatives are to the left of 0. Those are not part of this set. Now we are in the, what do we call these? Integers. So it's not closed under subtraction. Does that make sense? Integers have more in their set. They include the negatives. Now, not every integer is closed under every operation. Addition, yes. Subtraction, yes. Multiplication, yes. It's not closed under division. Why? Because if it doesn't divide evenly to become a whole number, 12 divided by 2, that stays under integers because it's a counting number, even. It comes out even. That's a whole number. Okay? But if it doesn't come out even, like 12 divided by 7, or a number where the top is smaller, like 1 over 2, these are not integers. Nope. So it's not closed. Integers are not closed under division because not every solution, not every quotient will also be an integer. What set is this where you've got a number over a number? Don't just say fraction. We call these the rational numbers. That's their name if we're talking about that set. It's less inclusive, so it's out. We show it outside the integers. Every rational number, every integer is a rational number. Every whole number is an integer. How could every integer be considered a number that doesn't come out even, or has a denominator more accurately? Because even whole numbers, like 6, okay, technically has the bottom number 1, which makes it a ratio or rational number. So that's the next highest level. Rational numbers are numbers that can be expressed as a ratio or a division between two integers. I like looking at them on a number line to understand that rational numbers come in between. This is a mistake here. This should be where the 2 is. They're the numbers that come in between the whole numbers. I don't even know what these are here for. Like 1, that should be negative. -1, -2, -3. Okay, between those integers, we've got like -1/2. -5/3 technically is right around, close to -2, about 3/4 of the way between -1 and -2. It's not super obvious when you look at it. We'll talk about how to make that easier to whittle down to something in lowest terms. 7/3 comes between 2 and 3. Okay? These are the numbers that come between the integers or the whole numbers or whatever. Rational numbers. Is -3 an integer, rational number, whole number? Which ones? -3, so not a whole number. Yes, an integer, which means yes, a rational number. 2. Is that a whole number? Yes, and since whole numbers are inside of integers, which are inside of rational numbers, that means those two are also included. It's a whole number, so it's an integer and a rational number. Might be easier to go this way to determine how far can you include them. 3/4. Is that a rational number? Yes. Now we decide, is it also an integer, right? We go from here to here. No, which means we can't go any further. It's not an integer, so it's just a rational number. We draw dots on the number line to graph numbers. To graph 3/4, we go 1, 2, 3/4 of the way to 1. If it were 1 3/4, we would go to 1, then graph the fraction portion after that. 1, 2, 3/4. That's 1 3/4. It's called a mixed number. We can also show rational numbers as fractions. You can write fractions many ways, not always in lowest terms. Just depends on how many cuts you have. This is the simplest version of a half, or 0.5, right? No cuts. Lowest terms. Most accurate. Worth the same amount of pizza per se, if we cut that half in half. Now it's 2/4, just not lowest terms. We can make that smaller to show it with no cuts. And continue to add cuts, now 3/6, now 4/8. These are all equivalent, meaning they're worth the same value. But they aren't all lowest terms. Only 1/2 is. You can also think of equivalent fractions on a ruler. How many inches is this? 1/2 inch. You can tell because this is only bigger. The only bigger one is the full. So if it lines up with there, that's worth a 1/2 inch. It's halfway from 0 to 1. But it's also 1, 2, is that where those are? 4th inches? 2/4 inches? No. Yeah. Kind of looks weird. I think this is actually, I'm sorry. I just realized those are eighths. It's 4/8. But let's just do the inches, the fourths. This is a 4th right here. Surprised that it's shorter than the eighths. Kind of confusing. But if I count 1, 2/4, and I know those are fourths because the rest of the way, it equals 4 divisions to get to 1. 2/4 is also equal to 1/2. And 4/8, 1, 2, 3, 4/8 is also equal to 2/4, which is equal to 1/2. They're all equivalent, worth the same value. But we want to reduce fractions when they're in our answers to their lowest terms, as they're called. For example, 12/18. If you just keep dividing by the easiest factor 2, you get down to 6/9, then divide by 3 4/6, then divide by 2 and you get 3. Oh yeah, you get 2/3 if you divided this by 3. But they're showing you can also start by dividing by 3. You can also start by dividing by 6, right? All right, let's look at what else they have for reducing. Okay, it can take a few steps to reduce a number down. Or if you divide by the greatest common factor, you'll get it by just dividing once. You can prime factorize the numerator and denominator separately. 4 is 2 times 2. So we write 2 times 2 here. 8 is 2 times 2 times 2. So we can write that here. And then you can do this, I'm going to use a different color. You can do this sort of crossing out, canceling. Cancel out 2's that are on top and bottom of each other. Cancel out pairs, leaving you with just the 1 on top and the 2 on the bottom. And you wouldn't do that with those easy numbers because you can just quick divide by the greatest common factor, 4 or 3 or 2. You don't need to prime factorize. But what about a bigger number, right? That could be valuable. Prime factorize 72 over 108. Okay, 72 prime factorized, if I did all the work, comes down to that. And the bottom comes down to that. So we cancel out pairs. That's why you want to write them lowest to greatest so that they're easy to cancel out. And all I end up with is this last non-matching pair, 2/3. It's a great way to quick reduce big numbers. I know you have your own ways too where you sort of use trial, error, and a calculator. But you could reduce a big fraction like this using prime factorization and your head, nothing else. Almost done. You can form equivalent fractions by multiplying a fraction by a fraction that is equal to 1. 2 over 2 is equal to 1. So we can go backwards. Instead of reducing, we can show another equivalent fraction that's not in lowest terms. This can be valuable for getting equal denominators or something, right? So what we're really doing is multiplying by 2 over 2, which is equal to 1. That's what they're trying to show with this behind silhouette of 1. And that's why we're not changing the value. That's why it stays equivalent. Because anything times 1 is 1. That's which property? Identity property of multiplication. An equivalent fraction to 1/2 with a denominator of 100. Okay, we want to get from 2 to 100. What gets me there? 50. The multiplier must be equivalent to 1. So we multiply 1 times 50 is 50. We can compare by making the bottom number or denominator equal. So instead of 2/3 compared to 3/5, we want to get an LCM or just multiply these together and instead show it as 15ths. To get to 15ths, we have to multiply by 5's on top and bottom, which is worth 1. So I have 10/15ths compared to, we want to get 5 to be 15. So I multiply by 3 top and bottom. Sorry, I shouldn't have done that. 9/15ths is equivalent to 3/5. Why change it? Because it's easier to tell when we have matching denominators. So, which one's bigger? 10 or 9? The left number. So 2/3 was bigger. Rewatch that if you didn't completely follow it. It's very important to understand how to do. Improper fraction means the top is bigger than the bottom. So it's top heavy. It's worth more than a part. It's really a whole with some remaining, unless it divides out evenly. So improper fractions are also mixed numbers that just haven't been changed yet. Like 2 3/4 is a mixed number. Well, what that really is worth is 11/4. We just haven't transformed it yet, right? Does that make sense? So you can make 10/3 into a mixed number by dividing. That's what this fraction bar means. Divide 10 by 3. That's 3 remainder 1, or 1 over the divisor. 3 1/3 is equal to 10/3, but it's a mixed number. They show this doing it this way. B will come out even. 12 divided by 6, you can tell right off the bat. You don't have to really do all this work. It's going to come out evenly to 2. That's why we call it a whole number. Answer. Okay, so with all that talking, I'd like you to do a lot of these as well. Let's do C, D, G, H, I, J, L, and the other ones below L, which were M and N. Okay? One more time. C, D, G, H, I, J, L, M, N. Best of luck. Work hard.